Welcome to section 11.2, Techniques for Evaluating Limits. So hopefully you've looked through your notes already and seen that we basically have three different ways to evaluate limits. First way we're always going to check is direct substitution. So if you can plug it in and get a value, great, that's wonderful. You don't have to do any work after that. If that doesn't work, we're going to try factoring out, or factoring and then canceling out that factor that is giving us an issue. Or the third possibility is going to be rationalizing the numerator and then factoring out and then direct substitution. So the first one we're always going to try is direct substitution. When we get indeterminate form, 0 over 0, it's the only indeterminate form we're going to cover this semester. Next year in calculus they'll talk about the other forms of indeterminate form and how you can deal with those. So first thing I'm going to do is I'm just going to try to plug in pi for this problem and see what happens. As soon as you plug in what you were looking for, as soon as that x value is equal to pi gets plugged in, the limit notation gets dropped. So, because you're actually then evaluating the limit for that specific value. Oh, cosine of pi is not indeterminate, it's not 0 over 0, that's for sure. So my students know that I always take out a whole bunch of little tiny pictures whenever I do this. Especially when it comes to trig, I know that pi is over here, and I know that cosine of that value is always going to be the x, which is -1. So what I know is I didn't get indeterminate form, I got something that worked out pretty nicely. So my answer would be the limit as x approaches pi. And again, if you keep this all kind of situated the way I have it above, with an equal sign trailing, you're fine. So for me, I just want to go ahead and rewrite it so people see that the limit as x approaches pi of cosine of x, my original question, is really that -1 value. Now let's take a look at the next one. Again, I always try direct substitution first, so let's plug in that 5 and see what happens. So the limit notation disappears because I'm plugging it in. So I get 5 squared minus 7 times 5 plus 2. There's no denominator here, so I'm not too concerned about indeterminate form at all. Actually, I'd be a little surprised if it showed up. So I know that gives me 25 minus 35 plus 2. 25 minus 35 is -10. -10 plus 2 is -8. So I'm satisfied with my answer. I'm just going to go ahead and bring down the notation so you can see exactly what this means. So the limit as x approaches 5 of my original function, which was x squared minus 7x plus 2, does give me -8 when I plug it in. So direct substitution is nice. Doesn't always work, but it's good to try first. Moving on to my next problem, I definitely see an issue with this whole -3, but let's try it anyway. So I'm going to plug in my -3, which means I'm going to drop the notation itself. So I get -3 squared plus -3 minus 6 all over -3 plus 3. Okay, I get the 0 in the bottom, which is exactly what I'm looking for. Remember, indeterminate form for us this year, the only form, is going to be 0 over 0. Now I take a look at the rest of this. The -3 squared is going to give me 9. Then I have a -3 and a -6. Do the math on the top. I do in fact get 0 over 0. When you get 0 over 0, it's basically telling you that there is a factor that you should be able to take out, something that they have in common that will eliminate that indeterminate form. So back to the original. I'm not going to plug in -3 yet, which means I need to keep my notation. So the limit as x approaches -3. If I take a look at this, that's factorable. The top is going to give me x plus 3, x minus 2. And lo and behold, there are the factors that match. It's the x plus 3's that are causing the problem. So if you take a look at this now, if I were to plug in -3 here and -3 here, top and bottom, that gives me the 0 over 0. That's why I'm getting indeterminate form. So let's just get rid of them. And we'll simplify this thing out. So this is going to give me the limit, still not plugging it in yet, as x approaches -3. Of x minus 2. Now I feel comfortable plugging it in. If I plug it in, lose the notation. Just plug in the -3. -3 minus -2 That's now -5. That is not 0 over 0. So my final answer would be the limit as x approaches -3 of my original that was given to me, which was x squared plus x minus 6, all over x plus 3. And after I did my dividing out and then my direct substitution, I ended up with -5. All right, let's move on to the next one. Same type of problem, so I'm just going to go ahead, try direct substitution, always first, see if it works. Just because it looks like a fraction doesn't necessarily mean direct substitution is going to fail. Sometimes it works, so plug it in. Always try direct substitution first. So I'm going to go ahead and just plug in my -1, although I'm a little hesitant because that bottom is definitely going to turn into 0. Now, if the fraction does not turn into indeterminate form for us, 0 over 0, but it turns into something else over 0, at this point, the only tools that you have would be to be able to graph it and then take a look at it. Next year in calculus, they'll give you other ways to approach a problem that doesn't turn into indeterminate form, but you do get that 0 in the bottom. So we're looking specifically for indeterminate form here, and hopefully that'll work for us, which it does. So we get 0 over 0, which means direct substitution doesn't work. So we got to do a little bit of work. So go back to my original. If direct substitution doesn't work, the next thing I'm going to try is factoring out. So the top looks factorable to me. So I've got a 2x, and an x, and a 3 and a 1. And there's the issue. That x minus 1, top and bottom, is what's going to give me that 0 over 0 for my direct substitution. So let's get rid of it. Now, rewrite what we have. Still not plugging it in just yet. And all we have left now is the 2x minus 3. Once you plug in the -1, remember that the notation goes away, so that whole limit aspect of it disappears. So it looks like we get -2 minus 1 is -5. Interesting. We got -5 twice in a row. Two completely different problems. Yeah. Not necessarily something to expect, just interesting. So take my original problem, 2x squared minus x minus 3, all over x plus 1. And my final answer, when I plugged it all in, I got -5. So again, I did direct substitution. That didn't work. I needed to make sure that it was indeterminate form first, though. Then I went back to the original problem and tried factoring. And that gave me something that I could cancel out, which is good. So direct substitution then worked after that, and then at the very end, just kind of pull it all together. Okay, so do the exact same thing here. I'm just going to go ahead and plug in 0. And then sometimes with the direct substitution, now I know for me personally, I'll have to ask Mrs. Lovett if she's the same way. For me personally, I don't need to see that you've plugged in using direct substitution before you move on to one of the other ways to evaluate the limit. Of course, you want to make sure that you have always checked direct substitution first, but if you don't show that, I'm fine with it. My expectation is at this point in your math career, you can actually plug numbers in your head and do a little bit of math in your head. So, especially with this one, because I get the square root of 1, which is 1, minus 1 over 0. This is clearly going to be indeterminate form, 0 over 0. So I'm just going to do the same thing that I did before. However, I don't see anything that I could factor out on the top and the bottom this time. What I see is I see a radical. For me, that means I'm going to rationalize. Now, when we go through and rationalize with limits, we don't rationalize the denominator. The denominator is not the problem. It's the numerator that's the issue. So I'm going to multiply the top and bottom of this thing by the conjugate of the numerator. So remember, you flip the sign between the two terms. Don't flip the sign inside the radical. That doesn't do you any good. It actually creates a larger mess. So I went ahead and multiplied that. Let's go ahead and see what this turns into. So again, keeping my limit notation because I haven't actually plugged it in yet. It's not until you actually plug in, do the direct substitution part, that you're going to actually get rid of the limit notation. So on the bottom, I'm not going to multiply it out. I'm just going to put the x on the outside because chances are that x is going to cancel. So let's just go ahead and push this all together. And then for the numerator, I am going to go ahead and multiply it out. So I know that x plus 1, root x plus 1 times root x plus 1, excuse me, is just x plus 1. So the roots cancel. I also know because of this whole conjugate business that it does look like a difference of squares. So the root x plus 1 times 1 and the root x plus 1 times negative 1 are going to cancel. I'm just going to left with that negative 1 at the end. So I know that my 1's are going to cancel here. I'll go ahead and continue this down. Still haven't plugged in the 0. Just going to copy down what I have. So I have x over x times root x plus 1 plus 1. I have x's on the top and on the bottom that now match each other. I can go ahead and cancel those out as well. That was the issue. So there's my factoring out now. So I've rationalized, that was the first part. The second part is now I can cancel out or factor out. Now, remember, whenever you cancel something top and bottom in a fraction, you still have something in the top. It's always going to be a 1 if you don't see anything else there. So make sure that you don't turn it into a 0. Now I'm going to plug in my 0 and see what happens. So again, I'm plugging in the 0, which means the limit notation disappears, and I get 0 plus 1 plus 1. However, I know that the square root of 1 is 1, plus 1 is 2. So I know my original problem, the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x just gave me a half. So again, I tried direct substitution first. So back up here, I tried direct substitution. That didn't work. I got indeterminate form, which means that I would definitely try to factor or rationalize. Then I went through and I rationalized here. Then I noticed that I could factor out here. And then finally, once I factored out, I could try direct substitution. After doing all 4 of those things, I was now then to figure out what the limit was as x approached 0. Not too bad. Again, includes 4 different things that you're going to need to do. All right, moving on. So this problem is a little tiny bit different, but it looks like stuff that we've been doing the entire year. We have fractions in fractions. So I wouldn't say necessarily that this is a rationalizing or a factoring out. I would say just kind of clean it up a little bit first. You can go ahead and plug in the 0 because there's no point in cleaning it up if direct substitution actually works. So if I plug in the 0, notice the limit notation is disappearing. I'm just going to go ahead and plug the 0 and see what happens. Well, I get indeterminate. I get 0 over 0. So that's telling me that this is definitely an issue. Oh, not 1. Let's turn that back into a 0. Then, I think I'm just going to go ahead and clean this up a little bit. So for me, I'm going to go ahead and get a common denominator on the top. So the first fraction needs the 4, and the second fraction needs the 4 minus x. I am going to use parentheses because that's subtraction, so I'm going to make sure that I distribute it when I actually put it together. And then I still have that denominator of x. So if I put this all together, looks like I get the limit as x approaches 0. My 4's are actually going to cancel because they're being subtracted. So those are going to disappear. Let's get rid of those 4's. But then I get this minus negative x, which just gives me a positive x. So I get x over 4 minus x, 4 times 4 minus x, all over, and I'm going to go ahead and make the bottom look like a fraction as well. So throughout the year, we've talked about, at least in my class, I know we've talked about, if the denominators match in a complex fraction, all the denominators match, you can cancel them. Same rule applies with the numerators. So if all the numerators match, you can go ahead and cancel those as well. So you have the numerator on the top and the numerator on the bottom are the same. Just get rid of them. Those go away. Now, remember, just like the previous problem, if you cancel something, it doesn't look like you have anything in the numerator of a fraction anymore. You definitely have a 1. So this is going to give me 1 over 4 times 4 minus x. Notice that I didn't do I did try direct substitution, that didn't work. I didn't try rationalizing because these are fractions, you don't rationalize fractions unless there's a radical in them. But what I did do, by matching the denominators, I ended up factoring out because I have those x's matching. So now, let's try direct substitution again. So if I plug that in, notice I'm losing the limit notation. I get 4 times 4 minus 0. Well, 4 times 4 minus 0 is just 1/16. And that gives me a nice answer. Not 0 over 0 anymore. Take my original problem, and I just write down what my answer is. So the limit as x approaches 0 of my original function, which was 1 over 4 minus x, minus 1/4 all over x, and I ended up getting 1/16 at the very end. All right, let's take a look at the next one. All right, so here we go. I only want to come in from the left-hand side, and with absolute values, we haven't really done anything other than graphing. So I'm just going to take a second and graph that for a second. Okay, so it looks like a lot like the graph of the absolute value of x over x from the previous section, except now it's being multiplied by 2. So all of my y values that were +1 or -1 are actually being stretched up to +2 or -2. Now, I only really care about the limit as x approaches 0 from the left. So I'm going to come in from the left-hand side and just take a look at this thing. So as I come in from the left, it looks like it's approaching that -2 value. Now remember, it doesn't have to get there. If it does, it's great. If it doesn't have to, though, so remember it's all about the approach. So as we come in from the left-hand side, just by looking at the graph, it looks to me like it's going to be -2. So the only work that I would show for this one is actually the graph. Oh, no, we've got the exact same graph. So let's go ahead and graph that one as well. Let's just take a look at it from the right. So I just went ahead and regraphed it on this screen so we can take a look at it. I want to come in from the right-hand side. Remember, I'm approaching 0. So as I come in from the right-hand side, it looks like the value I'm going to be approaching, not necessarily attaining, but approaching, is +2. So from my graph, again, this is a lot like what we did last unit itself. So I know that this is going to be +2. All right, let's take a look at the next slide. So on the previous 2 slides, we had from the left and from the right. From the left, it existed -2, or approached -2. From the right, it had approached +2. As we know, though, if you want an overall limit to exist, it has to exist from both sides. So the overall limit as x approached 2 itself wouldn't exist, but the left and the right do exist. All right, now we're coming into what we did at the very beginning of the school year, difference quotient. So what I want to do is I want to find the limit as h approaches 0 of difference quotient evaluated at 3. So I'm just going to go ahead and plug in my function just like you would have done first semester and just carry that limit notation with you. So let's do the first step. Okay, so all I did was plug in 3 plus h into the original function, so that's my first thing here. So my 3 plus h into the original function is the 3h quantity squared minus 1, and then for my second one with the 3 squared minus 1, that comes from this guy, just plugging in that f of 3. So now all I need to do is just do a little bit of algebra and clean this up. So I'm going to go ahead and multiply out the top and see what happens. So I went ahead and multiplied out the top, and I'll go ahead and combine like terms now. It looks like the 9, the minus 1, and the minus 8 are going to cancel. If you remember from first semester, whenever we did difference quotient, we expected everything to cancel except for the stuff with h's. Well, the expectation is going to be the exact same thing here. So the process really is almost identical, except now we have this limit we're going to be evaluating. So I think I'm going to go ahead and factor out my h at the same time. So I'm going to have a 6 plus h all over h. Remember, showing that whole canceling out of the h's. Now we have the limit as h approaches 0 of 6 plus h. Now plug in the 0. So it looks like we're just going to get 6. So what I would say is, going back all the way up here, that is equal to 6. So for the original function, so given f of x is equal to x squared minus 1, we want to evaluate the limit as h approaches that, and we got 6 at the very end. Again, notice the tiny little difference at the very end when we start plugging in the zeros. Now we have the actual difference quotient. Let's go ahead and plug this in and see what happens. Okay, so I have my difference quotient all plugged in. Now I'm just going to go ahead and multiply it all out. Not really going to show these steps just because this is something that we did first semester. So if you need to pause at this point to multiply it out, go right ahead. So remember, at this point, everything without an h, the expectation is that it's going to cancel. If it doesn't, we probably made a mistake. So I see my x squareds go away, and that's good. My 1s, my 4x's go away, and it looks like everything else has an h with it. So I'm just going to go ahead and factor that h out. So I am using the technique of factoring out here, so which is something that we used for evaluating limits. So I'm just going to go ahead and take a second and factor that out. See if that's it. That's it on the top. And my h. Remember that those should cancel. And if we tried to plug in 0 right now, we'd get indeterminate form, which means we definitely have an issue, and we should then proceed with other ways to handle that whole indeterminate form. So factoring, dividing out, rationalizing, all that. Plug in the 0, it looks like we get 2x plus 4. Now, it's perfectly okay to get a statement here at the end that actually has variables in it. You just want to make sure that all the h's disappear because every h is going to turn into a 0. So at the very end here, we take this answer all the way back up. And I know that this is going to be 2x plus 4. All right. Next one, same idea. Let's go ahead and plug it in. So I have it plugged in. It doesn't necessarily look like something that we handled first semester. However, now that we've been talking about limits and rationalizing the numerator, this is something that we should be able to handle. So I'm going to take this, and I am going to go ahead, because I need the h's to disappear, I am going to go ahead and multiply by the conjugate top and bottom. Remember, you don't change the sign inside the radical, you change the sign between the two terms. If you change it inside, you're not actually going to get anything to cancel when you try to multiply it out. So let's go ahead and multiply this out then. I am going to take my limit notation with me because I haven't plugged it in yet. When I multiply root x plus h and root x plus h, I'm just going to get x plus h. The reason why conjugates are wonderful is because with the sign between them being different, it looks like a difference of squares. When you multiply the outer and the inner, they cancel. So all you get is the first two terms multiplied together and the last two terms multiplied together with a subtraction sign between them. So root x and root x is just x. I'm not going to multiply out the bottom, just like I did on the other problems when we were rationalizing. I'm just going to keep that out in front. And I have a root x plus h plus root x. You'll notice that my x's cancel. That's good. You'll also notice that I now have an h over an h. So this would be my now dividing out technique, or my factoring. So I'm just going to go ahead and copy down what I have. Cancel those out. Remember, whenever you cancel something, I know I'm repeating myself, but I don't want you to actually lose your numerators here. Whenever you cancel out something, it doesn't look like there's anything up there, there's always a 1. Haven't evaluated my limit yet, so I keep my limit notation with me. Now, remember you're plugging in 0 for h. Leave the x's out of this. So if I plug in 0 for h, it looks like I just get 1 over root x plus root x, because the h disappears. Well, those are like terms, so you can actually rewrite this as 1 over 2 root x. So then I'm going to take my answer from the bottom, pull it all the way up to the top, and there's my answer. So what we're going to be talking about in 11.3 is, what does this actually mean when you find the limit as h approaches 0 of the difference quotient? So now we're just working on the mechanics at this point, going back and reviewing difference quotient a little bit from first semester. If you have any questions, make sure that you ask in class.